Thank you very much for organizing this interesting symposium and even more for inviting me to take part of it. But before speaking, I would like to ask a question about the Schrödinger Institute. Where does this picture come from? Now, my compatriot Sylvia Wenmakers and I believe it comes from the North Sea in Belgium. It looks like that. And in fact, on his way from Austria to Dublin, Schrödinger was for a brief period professor in the University of Ghent, where Sylvia studied. And so it's likely that he was at the North Sea. Actually, Einstein was for a while at the North Sea in a place called the Haan, or Le Coq in French, on his way to the United States. Anyway, so Schrödinger was saying in his letters that the Belgians are nice people, happy like children, and indifferent to the rest, to what's happening in the world, which of course they couldn't be a few years later. But anyway, that's to start with a little story about Schrödinger. Okay. So that's the title. And so the question is whether irreversible macroscopic laws that tend to be irreversible can be deduced or reduced to reversible microscopic laws. And the definition, the precise definition will come later, but that's a familiar topic. And the answer, which will be the goal of this talk, that in a certain sense to be made precise, the basic ideas goes back to Boltzmann, but there are also many pseudo-solutions, confused answers, etc. And very little is on firm mathematical grounds, but the general picture can be given. So I'll do it within the framework of classical mechanics. So if you consider classical mechanics and you have a closed mechanical system of n particles in 3 dimensions, if I denote by bold q the vector of the position of the particles, q1 up to coordinates q1 to q3n, and p the momenta of the particles, then everything follows. Everything is determined. In particular, macroscopic quantities like the density or the energy density are functions of the microstate. It's important to realize that they are functions of that. Now, a simple example of a macroscopic equation, the only one I will consider, is the heat equation, or the diffusion equation, where U now is a function of x in R3, and, for example, is the density or the energy density. And that's an example of a macroscopic variable, and the same idea would be for Boltzmann equation, Navier-Stokes equation, any macroscopic equation you think of. And in many circumstances, I mean, this, for example, with boundary condition, or if U vanishes is a constant at infinity, then U will tend to a constant as time goes to infinity and stay there, which corresponds to the homogenization of a substance in a certain volume. Okay? So now the way I want to describe it is like this. Omega is the phase space. It's a subset of R where 6n is of the order of Avogadro's number. N is the number of particles in this room, and then you have 6 coordinates for each of them, position and momentum. And this is the big phase space. You can think of it as a constant energy surface if it's an isolated system, for example. And then I will introduce the macroscopic function, which is a function f that goes to a set which is a function which is in Rn, where each, for example, you take the real space, here I do it 2-dimensional, and you divide into small cells, and then you call f1 of x, fn of x, the fraction of the number of particles in each of the cells. Well, here there is only 1 particle per cell, but you can imagine cells with several particles. And it's clear that this number is a function of the particular microscopic configuration. If you know the microscopic configuration, then you can tell how many particles there is in every cell, right? And the fraction of that gives you this number. And the function u of x in the diffusion equation is a continuous approximation to f. Now you approximate that by a continuous function if you think of the density, for example. Now, of course, you could say, well, u is a function, therefore it has infinitely many coordinates. Okay, it lives in a space of function, a Hilbert space maybe, and so there are infinitely many coordinates. And what is this small n here, which is supposed to be much less than large n, small n is infinite. But of course, if you think of U as being reasonably smooth, then of course you think of it as being equivalent to a first Fourier mode, or better, think of it as an approximation of something which is really finite. Okay? And so that's what you call the macroscopic description, which is a reduction of the number of, of the number of variables. It's very important. A simple example is you take coin tossing. X, the microstate, would be a given sequence if you have n coin tossing, it would be head, tails, tails, head, tails, a given sequence of result. And f of x could be the number of heads or tails. That would be the macroscopic variables. That's the one which you are talking about when you speak of the law of large number. And that takes all the values from 0 to n. And so that, of course, is much, much less than 2 to the n. Okay? Now comes the main point. If I start with an initial condition, position and momenta, that's the vector x which encodes all the position and momenta of the system, then Hamilton's equation gives you a time evolution, which I write Tx, which gives you x at time t. Okay? That's well known that you have the flow of the Hamiltonian solution. Now f, the function f, will give rise to value f sub 0 if you apply f to the initial condition. It will give rise to a function, a value f sub t, if you apply it to the final condition, final, let's say at time t, okay? And now, of course, you have the map from f0 to ft. That's the macroscopic law. Okay, now you can ask, is the evolution of f under the macroscopic law autonomous, namely independent of the x that is mapped onto f? The same way that for the coin tossing, you can have many, many different x's corresponding to a different number of heads and tails. If you have, let's say, half heads and half tails, then could be many different sequences. Then you could have very different, many, many different microscopic configurations giving rise to the same macrostate. And now the question is it independent of the x mapped onto f? If yes, but the answer is no, but if it was yes, then you could say that the macroscopic laws has been reduced to or deduced from the microscopic one, right? Because you take your f0, you pick up any x0 in the pre-image under f, let it evolve according to Hamilton's equation, and then you apply f of t, and then you get the answer, okay? So that means that f is just driven by the microstate. Okay, is that clear? If the answer was yes. Now to explain why the answer is no, the microscopic law is reversible under time. Well, that's well known. So what I mean is this. If I introduce the operation I that reverses the velocities or the momenta at a given moment, so if I take x at time t, apply this, then let the time evolution hold for the same amount of time that we had here, and then apply I again, then I get back the initial condition. Namely, I reverse the velocities, and then, of course, the trajectory will follow its trajectory backward, and then eventually it will be the initial condition with the reverse velocities. So I reverse the velocities again, if you wish, and then I get the initial state. This is the law of reversibility of the microscopic equation of Hamilton's equation. And it's illustrated in this picture, which I will use several times. You take black and white balls, and they're very well ordered here. You let them evolve, and after a certain time, they are completely mixed. And here, and this is a computer thing, so of course on the computer you can do it exactly. You reverse the velocities here, and after exactly the same time, which is another 20,000, let's say, seconds, then you get back the initial state. Okay? So that's an illustration of reversibility. But the map f0 to ft is often irreversible, as in the case of diffusion. If you take diffusion, then the gas will spread, and then it will be homogeneous and stay there. Okay? Because it goes to uniform distribution in the ordinary space, in real space. And there is no operation like the time reversal I that leaves the diffusion equation invariant, since the diffusion equation is first order in time. Okay? Thus, the evolution of f is not autonomous. If f is, for example, the density, then if you take this picture, and you take this picture that you get from the time evolution here, Or take this picture with the reverse velocities, the density obviously is the same, right? So you have two microstates here, one which would be the one evolved from here and would more or less remain like that, and the one which has the same picture for the position, but different velocities because you reverse exactly the velocities that will evolve in that sense. So you would not expect from the macroscopic law, if I gave you this as the initial state, the macroscopic law will never lead you to such a state. Yet the microscopic law might. Therefore, the macroscopic law is not, strictly speaking, autonomous. The density being uniform here corresponds to different configurations, some of which follow an anti-thermodynamic evolution, follow a law that violates a microscopic law that violates the microscopic one, okay? The macroscopic one. So the evolution of the macroscopic variable cannot be autonomous. The basis of the solution is that the map F is many to one. As I said before, it's like, you know, when you take coin tossing, you look at every coin tossing and you look at the number of heads and tails, that's many to one. I mean, for every value, except for one of them, for every value of the average or the number of heads and tails, there are many, many sequences of microstate corresponding to that. And for every distribution of the density, there are many arrangements of particles that would correspond to, you know, so it's many to one. But, and that's the whole point, in a way that depends on the value taken by F. And think of coin tossing. If you take F, let's say the number of heads to be n, the total number of thrown, there is only one configuration, head, 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 okay? But if you take it n over 2, then it's well known that there are approximately 2 to the n divided by square root of n configuration. Number of, you know, of sequences of heads and tail is not one, but it's quite a large number. Almost all of them are of that form. So here is a picture taken from a book by Roger Penrose, which is really essential, and it's a coarse graining of phase space into region corresponding to state that is macroscopically indistinguishable from one another. So, well, the first problem is that for simplicity, I draw these things discrete. They are different regions. I mean, it's assuming that you discretize the macroscopic variable because usually they are continuous, and so my partition would be a bit mushy. But let's think that, for example, you take the gas in this room, and you bring a piston that puts half of the gas in one half of the room, all the gas, sorry, in one half of the room, or in another half, or a little corner, or something like that. And each of these configurations then correspond to a subset of phase space. This might be the gas in one half of the room. This would be in a little quarter of the room, etc., etc. Okay? And this thermal equilibrium corresponds to all the configuration where the gas is more or less spread uniformly in the room. Okay? Now, not only this is a bit schematic because it's discrete, like if there were only finitely many situations, which is not the case, but it's for purpose of illustration. But the other thing is that this is not at all drawn to scale. Not at all drawn to scale. Because if you had, for example, if you think of the gas in, you know, the fraction of the phase space occupied by this gas when you put all the particles in one half of the room, would be roughly 2 to the minus n, when n is the number of particles, and this is of the order of Avogadro's number, okay, and it's bigger for this room, but then, of course, this is minuscule, okay? So all those guys put together should be invisible if things were drawn to scale. That's to keep in mind. Otherwise, you don't understand that if they are invisible, then I can't give my talk, so I've drawn them bigger than they are, okay? And now comes the so-called solution. The so-called solution says that if you start in a very non-equilibrium situation, a situation where the gas is very concentrated in one part of the room or with very different velocities than the Maxwellian distribution or something like that, then it will evolve like this. This is the microscopic configuration. Maybe I should remind you, that this is, of course, in the big phase space, in omega. This is a description of omega, of the big phase space. And in the big phase space, the one point means the configuration, the position, the velocities of all the particles in the gas. And it evolves according to Hamiltonian law. And then I claim that it will enter regions of bigger and bigger space till it enters the thermal equilibrium and stays there for eons of times. Now, how do I know that? Well, the truth is I don't. This is why I say it's a scheme. You see, it's very likely because of the difference of scale. And of course, that's exactly what you observe. You take away the partition in this room, and you see the particles spreading in the room. Basically, it corresponds to the idea in thermodynamics. Voilà. The thermodynamics that you sort of go to the maximum entropy state given by the related to the constraint. If you remove a constraint, well, basically here I won't speak about entropy, although the entropy is just the logarithm of the volume that you are in. So, for example, the entropy here would be the logarithm of the volume here, and the entropy of thermal equilibrium would be the entropy of the logarithm of the volume there. But the point is that you just you just expect this behavior to occur, and in some models you can prove it, but the models are not very physical. But why should it be easy physically to study the time evolution of 10 to the 23 particles according to microdynamical laws? We have enough problem with a few particles, okay? I mean, the solar system of 3 particles and so on. So it's not that surprising that it's hard, but there are certain systems like billiards or some, cat string model and so on, which I won't go into, but you can easily devise systems that will actually do this. And then that's what you expect, okay? So the solution of the reversibility paradox, or the fact that the equation is not autonomous, and it's not, the time evolution of the macrostate is not determined only by the microstate to which it corresponds, is this, that if you take a given omega 0, you give omega 0, which is simply the preimage of the macrostate. So F0, let's say, if your initial density profile, or your distribution of particles in a box. And F is the map from the microstate to the macrostate, so F inverse is the map from the macrostate to the microstate. Okay, it's a preimage. The preimage is a set in the big phase space. Okay? And then I call omega 0 bar the good configuration, which is not all configuration, but for all x in omega 0 bar, the macroscopic law, the induced evolution, so if you start with that, this will go according to the macroscopic law, where this evolution is induced by the microstate according to the microscopic law. Okay? So what you would like to say is that the macroscopic law will be explained by the microstate, microscopic one, if essentially omega 0 bar is all of omega 0. So now, okay, I managed to do it. So because I have the formula on one side and the picture on the other side, and it's better to have both together. Okay, so here is the picture. So we start back with our enlarged, this is the subset of R6n. This is omega 0. This is all the particles, let's say, in 1/2 of the box. Omega 0 bar is this shaded area, which are the good configuration, those that will go and spread throughout the box. You can very well have particles that are in 1/2 of the box and will remain in 1/2 of the box. You could also orient the position, the velocity, so that they will go to a smaller part of the box. We'll see that later, why this and this. So these are the good guys. And this is the time evolution of the good guys after a time t, which puts them in thermal equilibrium. By definition, all those guys go to thermal equilibrium after a time t, which cannot be too large because of Poincaré's recurrence. But that I will ignore. The Poincaré recurrence basically says that almost every configuration there will eventually come back there. Okay? But ignore that if you're not familiar with it. Okay? Now apply my I operation, which, remember, flips the velocities or the momenta. It changes the sign of the momenta. So this set now is sent into this set. Okay? Now, this set is still in thermal equilibrium, as I showed you in my picture with the 40, with the time equal 20,000, and then you reverse the velocities. When you take the homogeneous situation, if you reverse the velocities, it's still homogeneous. So you're still in equilibrium. You take all the particles in one half of the box, you let them evolve, change the velocities, the density is still uniform. But those guys are not good anymore from the point of view of thermal equilibrium, because all of those guys will go back in that region, which is not what the macroscopic law says. The macroscopic law says that once you're in equilibrium, you stay there forever. Okay? So, in formula, this I, Tt, so Tt omega 0 is this, I is this, and this is a subset of the equilibrium state, but it's not in omega T bar, namely it's not in the good configuration, because if you let these guys evolve, then there'll be a subset of omega 0, okay? Since we are sure that we go to. But it's not a paradox, because you have to look at the size of those things. The size of I Tt omega 0 bar is omega 0 bar for two reasons. I preserves the size because it's just flipping the velocities, and Tt preserves the size by Liouville's theorem, just Hamilton's equation. Okay? Now, omega 0 bar, of course, is less than omega 0. It's a subset of omega 0. Now, omega 0 is much, much less than omega t. Okay? That's what I told you before. It's that bad. Okay? Omega 0 over omega t, the size okay? So omega 0 is minuscule compared to the thermal equilibrium. So that omega t, if you take now those guys, and you say that omega t may still be very small, omega t minus the bad configuration, namely all the configuration in equilibrium, minus those that will have a non-thermodynamic future, okay, can be still very small. And the mathematical problem is to show that this set is small for whole times, not too large again, because of Poincaré's recurrence. And that, of course, is a formidable problem, if only because if you really look at a finite system of particles, then if you really let T go to infinity, then you will have this recurrence of the motion by Poincaré's theorem, so you can't prove it. But you can then do a limit where you let the number of particles go to infinity and let time go to infinity. But at least the scheme is clear, and the reason there is no contradiction seems to be pretty clear. Okay, I'm saying that this view by Boltzmann is often misunderstood, and here are a few statements by some great physicists which I think more or less miss the point. For example, Prigogine and Stenger said irreversibility, so this is either true on all levels or on none. Either it's true at the microscopic level or on none of them. It cannot emerge as out of nothing in going from one level to another. Well, I'm just claiming that it does. Okay? Irreversibility, Born said, is therefore a consequence of the explicit introduction of ignorance into the fundamental laws. I don't agree with that. Everything I've said is perfectly objective. It's true that we don't know the microstate, but that plays no role. What our knowledge plays no role, okay? Heisenberg said that Gibbs was the first to introduce a physical concept which can only be applied to an object where our knowledge of the object is incomplete. Again, this, of course, sounds very Copenhagen, and it's not maybe a surprise given the authors, but I mean, I don't think it's correct. Bondi was an physicist, said, it's a sentence I like very much, it's somewhat offensive to our thought to suggest that if we know a system in detail, then we cannot tell which way time is going, but if we take a blur view, a statistical view, that is to say, throw away some information, then we can. But you see, this is a mistake. They're just a map. This map is perfectly objective. It maps the microstate to the macrostate. And the macrostate evolves according to whatever it does. It doesn't matter whether we know. Of course, the macrostate is throwing away information if you wish. But the macrostate is the only guy who is irreversible. But there is nothing contradictory there. I mean, there is no, it's not, I mean, I like this thing, it's offensive to our thought. I don't think it's offensive. And then, of course, again, Prigogine said irreversibility was due to our approximation to our ignorance. And that's pretty common view. Then I want to say a few words about, I'm almost done, but I want to say a few words about the misleading solution. Yeah, I still have time. It's ergodicity. Ergodicity says that almost every trajectory in the big phase space, omega, will spend in each region of that space a fraction of time proportional to its size, the Lebesgue or the Liouville measure. Okay? So ergodicity says that you go almost every trajectory, if you take the big phase space, omega, every trajectory will go and visit every part of the space and spend time equal to its size. It shows too much and too little. That's why I think it's irrelevant. It shows too much because you are not interested in the time spent in every tiny region of the phase space omega. You see, ergodicity would tell you that if you put all the particles in one side of the box, of course they will spend a lot of time in the homogeneous, but they will also go in a little corner of the box there. They will also all go in a little corner there, because these are part of the big phase space, and they will explore every part of the big phase space. So why kill yourself to try to prove something which you never observe and which you don't want to predict, namely that particle will go to every tiny region of the phase space. It's too little because ergodicity says nothing about timescales. And of course it could not, because it predicts that the configuration of the big phase space will be so that all the particles will someday be in a little corner. But which day? Well, after eons and eons of time. So it doesn't tell you anything about timescale because it tells you things about every observable. So you could say what you want to show is that the macroscopic quantities reach equilibrium reasonably fast. The macrostate. But the macrostate, that's not every function on phase space. Ergodicity applies to every function on phase space. The macrostate, of course, will reach equilibrium pretty fast, for the reason I explained here, because of the differences of size. Once it's there, it's there. I don't care that the ergodicity shows me that it will go back here and there and there and there. Okay? The macrostate will go to the equilibrium because the equilibrium occupies so much, the equilibrium value occupies so much bigger part of phase space than the microstate. And that's the point. So ergodicity is just irrelevant. But now you could say, that's the point I thought that was in the title, so I should say something about what's in the title. Does this explain irreversibility? And the second law, which I've not discussed, but which is a version of that, simply entropy increases is related to this irreversible behavior. Now the question is, what do you mean by explain? If you don't tell me what you mean by explain, then I can't tell you whether it explains it or not. And explain is like reality, it's like existence, it's like objectivity and so on. It's one of these basic notions that if you don't know what it means, then you simply don't know English. I mean, there's a certain problem I have with definition. When I discuss quantum mechanics with idealists, they say, well, what do you mean by exist? Well, I mean by exist, that's a basic word. I mean, I can't define it in other words because then you can ask me what these other words mean, right? I could say it is, but So I will explain what I think is explaining. And in a deterministic framework, if I take my, I will not drop it from here, I drop it there, then I start, imply that the state A at time 0, like my pen was here, Yeltsin's time B at time t, it's on the table. Then I would say that B at time t is explained by the laws and by A at time 0. Okay? That's the causal, every explanation, if you want to explain the weather today, then you say, well, yesterday it was so and so, and then there are certain laws of, not climate, but meteorology that tells you that it's going to be today. And then you say, well, but now we still explain A, what happened yesterday? What was the cause for yesterday? Well, there's something the day before, and so on and so forth. Ultimately, your explanation always goes back to to the origin of the universe, if you really want to be rigorous. But nevertheless, if you think about every causal explanation you ever think of, it's always like that. You have a state that deterministically implies a state B, and then B is explained by A and the laws. That's what I suggest. Then in a probabilistic framework, which is the one we are talking about, I make the following suggestion. F0 is a macro state at time 0. Then there is a natural measure on the corresponding set of microstate, which is the pre-image in the big space here. Okay, I take F and I take the pre-image. And I define a measure which is the maximal entropy measure. That I think is a natural measure because the information I have is the value of the macro state. And then I take a certain measure on the microstate, which is just the indifference principle, if you wish, in modern formulation. Now, if with large probability, this is my business about omega 0 bar being a large subset of omega 0, if you wish, with large probability, the macrostate obtained from the evolution of the microstate equals Ft, then I would say that the initial macrostate and the laws explain the final macrostate. Okay? So what I'm saying is that if I take, again, the particle are all now in part of the box, a part of this room, and then I let them spread, then I explain why they are uniform by saying, well, they started in that part of the box. And the overwhelming majority of the microstate corresponding to that description, there was this evolution towards an homogeneous situation. And I would say another way to say that one would explain Ft by a Bayesian reasoning, one would have predicted Ft knowing only F0 at time 0 and the microscopic laws. Okay, this is a suggestion. Now, of course, you may disagree, but there is a, this is a basic concept, so I can't really, we can discuss that. But now, of course, there is a problem once you have understood that, and that's something where I learned something yesterday, but I did not assimilate it. Why doesn't this argument apply to the past? If you go back to my picture with this 40,000 time and you reverse the velocities here, now if I give you something in between, like this description, where white and black balls are not completely mixed, and I ask you, what does this come from? What is the past of that? Well, if you look at my picture, we say it's there. But if you apply the reasoning I did, which is to say that this in the future will go there, then by reversibility, you should say that in the past it will go there. And in fact, it's far more probable that you start from this situation and by a fluctuation of infinitely small probability, you go to this. Very small. You can say, well, this is very improbable. Yes, but if you start from that, then it's even more improbable. So this situation is extraordinarily improbable even compared to that. So the logic of what I said is actually saying that this should come from that and not from that. But in practice, we always know that it comes from a situation like this. We never see a fluctuation of that form. But why do we know that it comes from a situation like this? Well, because somebody prepared it in that situation. Somebody outside of the system prepared it. Somebody who is not in equilibrium, us. And of course, this is the, you see, there is a, as I said, there is a serious logical problem you could apply to the past. And the only reason you don't apply to the past is because you say there is an experimentalist who has prepared a computer, has prepared it. And the real problem is then you always explain this increase of entropy by saying that in the past you were in a low entropy state, and the low entropy state in the laboratory was prepared by another low entropy state, which is a human being, and so on and so forth. But then where do they come from? And that's, again, a picture from Penrose's book. The way it works, there you see the experimentalist, he's eating, he has plants, animals, and so on. And the point is that the sun keeps all this business going by sending few, well, not very few, but high energy photons and emitting many low energy photons. And in between, there is, those have lower entropy than those. And so there is an increase of entropy in the emission. And in between, you make those people alive. And that's how it works. But then you can say, where does the sun come from? And then, of course, you are going back to the beginning of the universe, and then you have another picture, which is that you take the phase space of all the microscopic configuration of the universe, and then God, that's God, is choosing, in case you don't know him, he is choosing a microstate with very, very small volume in the total volume. I mean, I'm not sure what that figure comes from, but anyway. And that, okay, I finished my talk by saying there is no good answer to that problem, but yesterday, Sylvia Lenmacher referred to her work and other people's work that there is a way to think of it without appealing to improbable original states. But I've not digested since yesterday, so I will finish with this picture. But I think that's the problem. Anyway, the origin of the low entropy state is a real problem. But the explanation of irreversibility, which is confusing a lot of people, and it's very confusing when you teach these things, is not. That's what I would like to conclude with. And it fits, of course, in a Bayesian view of probabilities. Okay.